Gravity. That's what we're talking about. Gravity. You've lived with it your whole life. Ever since you were a little kid, people have told you about gravity. It explains why things fall. You've probably known gravity also as the force of gravity. We're going to talk about that because we're already familiar with it. So let's start with what we know or are willing to accept readily because we are comfortable with the ideas about gravity. And we're going to use gravity as an example of a force. So we're going to, by me starting with something familiar, we're going to say hello to forces, which is section 5.1. And more importantly, we're going to get to the bigger questions like, what is a force? Why is it important? And very practically, what are the units of force? Because in physics or science in general, if you can quantify it and assign units to it, it's real, it's physical, okay? All right, we have some phrases up here. Well, we'll fill them in, but I think you can see that they talk about gravity as doing some things that you already know it does. And again, I'm not going to argue that gravity is a force. Why? Because you're already comfortable with it. The force of gravity. Okay, so if we just already associate the word with the thing, then we'll use the thing to understand what the word means. Hopefully that makes sense. Let's go. Gravity does what? You just studied free fall. Does what to free fall? Okay, and just as a reminder, what's free fall? It's a downward acceleration due to this thing. So if this is due to that, then gravity causes free fall. And in free fall, the main evidence of something in free fall is that it has a downward acceleration. When we were little, or maybe growing up, you also maybe came across a phrase like this. What does gravity do to things? Well, I don't think you would say it causes them to free fall, right? If I told you it did something to an object downward, hopefully you would say it pulls an object downward. Not only that, furthermore, you know, this is the part where it gets a little tricky. Okay, I think we all grew up being okay with definitely the second one, pulls an object downward. So, you know, if this was a bowling ball, right, our experiences of gravity is we'd let go and it would be pulled toward the earth, downward. Okay, now that we studied motion, that downward motion, okay, we realize is more specifically defined or precisely defined as a downward acceleration. Its velocity is changing. We also have met the strength of gravity. Bowling ball. If this was a bowling ball, I would say gravity's pulling on it more, simply because I could feel this thing squishing down on my hand, and to keep it from falling, I gotta push harder up, right, to counteract the pull of gravity. But I can sense that strength. We've all known what the strength of gravity is called. We call it weight. So the bowling ball weighs more than a ping pong ball, or an air-filled ball, right? A bowling ball has more weight. What does that weight measure? Well, you could say it's a measure of how much you have to, it quantifies what you have to do to make it stay still, right? I got to balance, I got to push against its weight. But really, it's a measure of how strong gravity is pulling on it. So it's the strength of the pull of gravity. So the key thing about this phrase is it nudges our mind to think or to remember that the pull has a magnitude. I could pull with more strength, less strength, etc., etc. When gravity is doing it, we call it weight. Okay, so that's, again, gravity is a force, and it behaves like this, or it has this nature. So if we're going to continue calling it a force, then it means all forces have this kind of nature. We can also quantify what weight is. I mean, in everyday life, we've grown up putting a number to weight. So we know that it can be quantified. Also as a unit, in the American customary system, it's pounds. We got to figure out what it is in the metric system and why it is. But first, what's the language of physics? Math. So we have to ask, from a physics perspective, is there a math model for weight? Let's see. let's think about the behavior or the pattern in weight or things that affect weight, and maybe we could get a math model out of it. Well, we're walking into this conversation comfortable with the idea of mass, right? The amount of stuff making up an object. And we know that the more mass I have, the bigger the weight. So we already like that idea. So we want to make sure our math model is consistent with that. Now, weight, though, does the weight of an object change? Yes, because we all grew up with the Earth versus Moon thing. So on Earth, let's go with on Earth, we accelerate downward at, from the free fall section, you might have met the number 9.8 meters per second squared. This is experimentally verifiable. You just got to measure, you let something fall, you measure its motion, right? You could measure its position with respect to time, and et cetera, and then you could figure out how much it accelerated. You could figure out its change in velocity, and you're good to go. You can figure out its acceleration. On the moon, it's about 1/6 of that. So this divided by 6 is 1 point something. I'm going to say it's around 6 meters per second squared. I don't know how accurate that is. But the main thing is that on the moon, apparently a bowling ball will weigh less. And that's coincident with the fact that on the moon, the bowling ball will accelerate downward at a smaller rate. It'll accelerate slower than on Earth. Okay, so, and we notice that coincidence, right? So that weight seems to differ. The weight of an object can change, not just based on its mass. If I keep the same mass, same bowling ball, the weight also matters due to acceleration due to gravity. So from the free fall section, you know that we have a special symbol for acceleration due to gravity. It's little g. So this number, without any subscript, if we just use g, our convention will be that we're on Earth. For the moon, we should differentiate that. So we might write gm or g moon, just to let the reader know that we're not talking about Earth. Okay, so our weight also depends on g. So the more g is, the faster something accelerates when I drop it, the more weight it has. There's the behavior of weight. Well, we could quantify this. It looks like more mass, weight increases. More g, weight increases. Well, there's a simple way to mathematically capture that. If we start with weight is equal to mass times g, it captures this pattern, this behavior, right? It models this behavior. So there's your equation for what weight is. Now, if we have an equation for weight, we can also get its units. So let's knock this one out because it's not that exciting, okay? It's just details. We can figure out what the units are. If UDA, right? Unit dimensional analysis, the units match the math. So the units for mass are kilograms. The units for little g, which is an acceleration, is meter per second squared. So if we multiply them together, that's our unit for weight. How anticlimactic, right? A kilogram times a meter per second squared. Please note how we verbalize this. Kilogram, meter per second squared. Not kilogram per meter per second squared. So, no. Okay? No per. Bad. There is no per here. What would be a kilogram per meter per second squared? Mathematically, that's mass divided by an acceleration. Right? So, mass divided by g. But our math model doesn't say that. It says m times g. So, these are the base units of weight. And we get tired of saying that. Imagine if you had to keep saying, I weigh 170, well, not 170, I weigh 700 kilogram meters per second squared. Oh, really? Mr. Canyo, that's a little unhealthy. You really should drop your weight down to like 500 kilogram meters per second squared. Or I'm going to lift some weights. How much can you bench press? 250 kilogram meters per second squared. Actually, that number's wrong. It would be more like 1,000. 1,000 kilogram meters per second squared. We don't want to keep saying this over and over again, so we give it a nickname. The nickname, the nick symbol, is N. What's that stand for? That's the symbol for the Newton. So 1 Newton is equal to 1 kilogram meter per second squared. Okay? Those are the units. All right, we're almost done. You met your first force. Actually, you met it before, right? It's just gravity. We gave it a new nickname, weight, but we also have a math model for it now because this works. This math model works, right? Makes sense to us. So if we broaden this a little bit, let's broaden it out. I'm going to keep that there because that's worth noting. But if we broaden this out a little bit, what is a force then? Well, if gravity is a force, and we look at all what it does, a force is just a push or a pull. Or in this case, since we use pull first, I'm going to say pull or push. The distinction between the two will vanish. That's why we say or. You could think of it either way, right? The second thing, why is it important? Well, what does gravity do? Causes downward acceleration. So if we broaden it in general, a force or forces cause acceleration. Why is that important? Well, because if you think about microscopic, macroscopic motion or changes, go really tiny, go really big, they're only interesting or things change when there's an acceleration, right? So if I'm on the freeway, let's talk macro, everyday life. I'm on the freeway, driving constant 50 miles per hour. Yeah, that's cool. It's safe. It's comfortable. But when does something interesting happen? When the off-ramp's coming up and I got to get on it. I have to do two things. I got to turn the wheel, drift to the right, change direction, and I have to slow down. Those are all changes in velocity. There's an acceleration. If you go microscopic, collisions of molecules, how do you produce heat? Well, molecules have to vibrate faster. Vibrate? Oh my gosh. My direction's changing over and over again. I'm speeding up one way, slowing down, speeding up one way, slowing down. All those vibrations. Massive accelerations. Big stuff. James Webb Telescope, out in the universe. Black holes, galaxies colliding. Interesting stuff happens only when there's an acceleration. Okay? Speaking of acceleration, acceleration is a change in velocity. Velocity is a speed in a certain direction. What do you call that? It's a vector. What about forces? Well, take a look. A force has a strength. There's a magnitude. Forces have direction. We can already, as soon as we say push or pull, your brain gets that there's a direction involved. So, a force is also a vector. So you've met force. Push or pulls that can cause acceleration. We'll talk about when that happens and when it doesn't. But it's also a vector quantity. The units are in Newton. And you met your first example of a specific force. We first met our first math model, W equals mg.